Testing. Welcome back, class. Today, our focus is going to be on exponents. This seems to be a really difficult concept in algebra for a lot of students. There's some rules that apply, and my goal here today is to try and make these rules a little more understandable, to try to make you understand why we make the rules that we do. This has to do with section 8.1 to 8.2, and I'll be assigning that this Wednesday. It'll be due then next Monday, which is, I believe, April 6th, right? So let's review some exponents here, and we'll look at some rules. And again, your goal is to try to understand why did they make the rules they did for exponents. The first is a definition of what exponents mean. If I have some number written in the exponent position, like 3 is here, what that means is that this number 4 is going to be multiplied times itself 3 times because I had a 3 there. If that number had been an 8, there would have been 8 4s here. Would have been a very large number. That's really the definition of an exponent. It's what the world agrees we're going to use worldwide. So for example, if I have x raised to the 3rd power, it means I'm going to take that x times itself 3 times. If I've got x raised to the nth power, it means I'm going to take x times itself. There might be a whole lot of them in here, but n times. That's a definition. It's what we just agreed to let that symbol refer to. But now, here comes the reason for our first rule. What happens if I have y squared and I'm multiplying it times y to the 3rd? Well, the y squared, by definition, would be the y times y. The y cubed, by definition, would be 3y's, and we're multiplying them. Well, notice when I'm multiplying these 2 y's times these 3 y's, it would be the same as if I have 5 y's in a row being multiplied. Because I have 5 y's in a row being multiplied, we say it's y to the 5th. But again, notice that that 5 could have been gotten easier than doing the y's here and the y's there. Could have been gotten by just simply taking 2 and adding 3 to it. Because that's what's really occurring, even though it's say we're multiplying, we end up adding the exponents. That's why in this one, even though I'm multiplying here, I'm going to be adding the exponents. It's going to be x to the power 5 plus 4. 5 plus 4, or it's going to be x to the 9th power. This one, it's going to be 3 plus 4 plus 8. 3 plus 4 plus 8, or it's going to be x to the 15th power. But again, looking back up here, when I had y squared, it was 2y's, times y cubed, which was 3y's. I ended up with 5y's being multiplied. That's why I got y to the 5th. That is the reason why we add. That is the reason why we get this first law. If you would like, I think it would be good to write these down. I'm going to be adding to these as we go. So leave some space below here. We're going to be adding a bunch of these. But notice I added a plus c. Even though I'm multiplying the bases, I add the exponents. So let's make sure we caught that then. From there, if I have x to the 11th times x to the 12th, that's going to be x to the 11 plus 12. That's going to be x to the 23rd. We add them together. Very important that we are very solid now on that first rule. I'll come back to this one, but let's first take some examples. Well, in this one right here, the 4 is not an exponent. It's just a number that stays out front. But now I have a bunch of x's being multiplied. This x to the 3rd, x to the 7th, and x squared. Because they're being multiplied, it means the exponents have to be added. So I have 3 plus 7 plus 2. I also have the y's here. I have y to the 5th times y to the 6th. I would need to be adding 5 plus 6. So my final answer is going to be the 4 out front. X to the power, I'm adding now, 3 plus 7 plus 2 is 12. 5 plus 6 is 11. So I added the exponents in that case. This time, I have a coefficient -3 and another coefficient 6. Those two numbers, -3 and 6, are not exponents. They are just being multiplied. So a -3 times 6 would simply be a -18. Now I'm going to work with the exponents, x to the 4th times x to the 8th. So the -3 and 6 were multiplied, but the x to the 4 and the 8 are going to be added. 4 plus 8 is 12. And the exponents of y will be added. 5 plus 7 also happens to be 12. This time there's no coefficient here, it's just 6. Just like up here it was just 4. So the 6 comes along all by itself. But now I'm going to do the x's. Think about what you would write for the power of x. It would be 4 plus 3 or 7. I'm going to go alphabetical order, so I'm going to leave the y next. There is only one y term here. There's no y's over there. So it's not going to change at all. It'll stay y squared. But I do have a couple of z's. I need to add the exponents. Here the exponent is 5. This one was not written, which implies that it's a 1. So I have an exponent of 1, and I've got an exponent of 5. 5 plus 1 will give me 6. And that would be my answer in that case. Is everybody comfortable now with why we add them? Super important that we're very, very confident in that. Next, this was where I'm multiplying. We added the exponents. Now consider this one once. Y to the 5th divided by y squared. Well, y to the 5th we know is 5y's being multiplied. Y squared is 2y's being multiplied. Well, this y would have canceled with that one. This y would have canceled with that one. And I would have been left with these 3 y's. Y times y times y, 3 of them, which we know by definition is y cubed. But I'm hoping by now you can see a shortcut rather than writing this all out every time, that we could have gotten that 3 back here from the y, a 5 and the 2 by simply taking the 5 and subtracting the 2. That would give us the y cubed. Repeating then, when I'm dividing, I have to actually subtract the exponents. Subtract the exponents. So for example, here, I'm dividing. I should subtract the exponents. 8 subtract 6, the top number minus the bottom one, and I end up with x squared for my answer. Notice though, sometimes we have a larger number in the denominator. So if I go 4 minus 6, I get a negative 2. But recognize what that actually means here. I'm going to do the long method here for this one. I had 4 z's in the numerator divided by 6 z's in the denominator. These would all cancel, and I would have a 1 left up there and 2 z's. 1 over 2 z's really is z squared. That's why this z to the 4th over z to the 6th is really 1 over z squared. But also, if I follow my rule, 4 minus 6 is a negative 2. That gives me a reason why, listen carefully now, that's why these two have to be the same. Is because when I do the subtraction, it's got to be the same as when I do the canceling like I did here. So that gives me a reason why we define negative exponents to be this, meaning if I have a z to the negative 4, it would be 1 over z to the positive 4. If I have x to the negative 17, it's 1 over x to the positive 17. Okay? I could also go the other way and say, what happens if I had x to the negative 3 down here? I can move that up into the numerator and change the sign and make it a positive 3. All of these are examples of how we define a negative exponent. That's why that rule now changes to add these two. The negative exponent can be written as 1 over x to the positive exponent. If I'm dividing x to the a divided by x to the c, we end up subtracting a minus c. That's of course opposite of this one. When I multiplied, I added. So when I divide, I'm subtracting. Some examples again, just to make sure that we are comfortable with this. If I have x to the 5th over x to the 3rd, I can use the subtraction. That would be 5 minus 3 or x squared. If, on the other hand, I had y to the 2nd over y to the 5th, I could subtract 2 minus 5, always the numerator minus the denominator. That would be y to the negative 3. But I also recognize that anything to the negative can be written as 1 over that to the positive. In other words, y to the negative 3 could be 1 over y to the positive 3. If your problems ask for you to write all answers in the numerator, then your answer would have been one like this, y to the negative 3. If they say write all answers with a positive exponent, you would move it down to make it a positive 3. Let's take a few more examples here. Let's go something like the following. X to the 3rd, y to the 4th, z to the negative 8 times x to the 2nd all over x to the 4th, y to the negative 11th, z to the 7th times z. Let's simplify this, and let's just say write all answers in the numerator. Put all answers in the numerator. Well, working through this, the x is being multiplied times x squared. So when I multiply, I add the exponents. So 3 has to be added to 2. but I'm dividing by this x to the fourth. When I divide, I need to subtract. So the 3 and the 2 added together will now subtract 4. The y's, I have a y to the fourth. I need to subtract because I'm dividing here, so I'm subtracting a negative 11. And finally, the z's. I would end up z to the negative 8 divided by z to the 7th and z to the 1st. It's not written there, but there's a 1 there. I got to subtract, so I take the negative 8. I'm going to subtract 7, and I'm going to subtract that 1. So my final answer then is 3 plus 2 minus 4 is 1, which I just leave it as x. 4 minus a negative becomes 4 plus 11, so I get 15. Z, adding those all up, I have a negative 16. If they said write your answer with all the exponents in the numerator, this would be your answer. But if they had said write them with positive exponents, then you would have moved the z down into the denominator and made it a positive exponent. This would be your answer if they said write them all with positive exponents. This one up here would be your answer if they said put them all in the numerator. And they might ask for either one. Okay? One other example. Let's just take 8, x to the 5th, y to the 7th, divided by 2, x to the negative 3, y. I wanted to emphasize this one because the 8 and the 2 are not exponents. So we do not treat them like we do the 5 and negative 3 and the 7 and the 1. These are coefficients. It's no different than 8 divided by 2, which is 4. So 8 divided by 2 will be 4. This x would be 5. Subtract the negative 3. 5 minus a negative 3 is like 5 plus 3, or 8. The y, these are exponents. 7 minus 1 would be 6. So keep in mind the coefficients are treated like numbers, but the exponents have their own set of rules. And it's crucial, again, that we have all of these down quite well. Unfortunately, now we're going to make it a little bit more challenging because of this next rule. Recall again, if I have anything raised to the third power, whatever is in there would be multiplied times itself 3 times, right? Well, we're going to put something in there that's a little more complicated looking. For example, I have a coefficient, a variable, and an exponent. But because whatever I put in there needs to be multiplied times itself 3 times, that's the definition of the 3 in the exponent position, I take whatever is in here and I multiply it times itself 3 times. Notice that means the 5, which is a coefficient, will be multiplied times 5 to get 25, multiplied times 5 to get 125. So I multiply all the 5s because they're coefficients. But the exponents, when we're multiplying, we add our exponents, so I get 4 plus 4 plus 4 to give me 12, right? Some real common mistakes. Some people might have multiplied the 4s to get 64 there, which would be wrong. Other people might have added the 5s to get 15 there, which would have been wrong. We treat the 5 one way, we treat the 4 another way. It's because the 5 is a coefficient, the 4 is an exponent. They each have their own rules that apply to them. Super important that you understand this principle, why the 5 was being multiplied times itself, why the 4 was being added every time. Crucial to get that difference. Okay? Technically, I would have it raised to itself 5 times. Technically, I've got 5 of these parentheses. That means that -2, which is a coefficient, would have been out front every time. -2 times -2 would be 4. 4 times -2 is -8. -8 times -2 is 16. Times a -2 is a -32. Notice that that really is the -2 raised to the 5th power. -2 raised to the 5th power means -2 times -2 times -2 5 times, giving you the -32. Technically, I got x to the 3rd in every one of these. So it's x to the 3rd times x to the 3rd times x to the 3rd. The 3 are exponents. So I need to add all those 3's. 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15. Then I have y to the -4 times y to the -4 times y to the -4, y to the -4, y to the -4. All of these -4's are exponents, so I add them. -4 plus -4 is -8, -12, -16, -20. That would be my answer right there. Now, a faster way we can do that, we could have said the -2 is raised to the 5th power. The x to the 3rd is to the 5th power. The y to the -4 is to the 5th power. When I have these x to the 3rd to the 5th power, I got x to the 15. Notice that 15 could have been found 3 times 5. Well, that's confusing because we've been saying all along you always add the exponents. Well, I would be adding the exponents if it was like this. That would be adding them. But when I have an exponent to another power, I multiply them. Super important that you get this difference. If you need to pause that and look at that again 3, 4, 5, 10 times over, big difference between those two. Big difference between those two. Okay? So let's use the shortcut method here. This will be 4 raised to the 3rd power. It's going to be x to the -2 raised to the 3rd power. It's going to be y to the 5th raised to the 3rd power. And it's going to be z raised to the 3rd power. This means 4 times 4 times 4, which is 64. Here I got a power raised to a power, which means I multiply -6. Power raised to a power means I multiply to get 15. This is really a 1 there, even though it's not written. 1 times 3 is 3. If I was told put all my exponents in the numerator, that would be my answer. If they wanted positive exponents, I would leave the positive ones right where they are, but I would have moved that -6 down to the denominator and made it a +6. What we've demonstrated there, here's adding to some more. Power raised to a power, I multiply. Even if it's a fraction, I would multiply this exponent times n and that one times n. I've done a number of these where this is a coefficient. That coefficient just gets raised to the n power, but a gets multiplied times n, a times n right here, and c gets multiplied times n. Let's see if we've picked up those examples once. I have 5 to the 3rd. That means 5 times 5 times 5, or 125. x to the 2 power raised to the 3rd power. That's an exponent raised to an exponent, which means we multiply. 2 times 3 is 6. Z to the power 6 raised to the power. It's an exponent raised to another power. We multiply. So I have 6 times 3 or 18. Here I've got x to a power raised to another power. I multiply. Negative 3 times negative 2 is a positive 6. And I got a z here to a power 4 raised to another power. I multiply. 4 times negative 2 is a negative 8. The number out front is a coefficient. X to the 6 times x to the 6, I'm multiplying, so I add 6 plus 6. Z to the 18 times z to the negative 8, I'm multiplying, so I add those exponents. 18 plus a negative 8 is 10. Again, super important that you can get, and why you see that I use the 5 differently than the other exponents. This one, a lot of ways you can think of this, but I'm going to try and break it down maybe as easy as I can here. The 7 is to the 2nd power. X to the 3 to the 2nd would be x to the 6, I multiply. Y to the negative 5 to the 2nd is y to the negative 10. 4 is to the 2nd. X to the negative 3 to the 2nd, that's a power raised to a power, so it's going to be a negative 6. Z to the 8th raised to the 2nd is to the 16th. So I end up with 49, 7 squared, over 16. I'm going to put everything in the numerator if you don't mind. So I'm going to take this negative 6, move it up. Or I could think of it as 6 minus a negative 6. Either way, I should get 12. There's only one y there. The z I would move up. It would become a negative 16. That's one form of my answer. We recognize 5 to the negative 2 is 1 over 5 to the positive 2. Or we could say 1 over 25. Simple enough. This one, if I were to simplify it, it would be, up here I had 7 to the 2nd power. Here I'm going to have 7 to the negative 2 power. X to the 3rd times negative 2 would be x to the negative 6. Y the negative 5 to the negative 2 would be the positive 10. 4 to the negative 2. X to the negative 3 to the negative 2 would be a positive 6. Z would be to the negative 16th. That would give me now, watch what I need to do here. This really could be changed now. Bring the 7 down. It would make it a positive 2. Bring the 4 up. It would make it a positive 2. Let's move the other things up into the numerator here once. This 6 would go up to the numerator, or I can think of it as division. So I take a negative 6, subtract 6. Either way, I get a negative 12. The y stays up there. The z, I'm going to move up to the numerator, making it a positive. So 4 squared now is 16, x to the negative 12, y to the 10, z to the 16, all over 49. It's a little tricky when you got coefficients to the negative power. Double check how I did this. 7 to the negative 2, 4 to the negative 2. I switched them and then got their numbers. Those numbers are frequently missed. These are the rules that we've developed so far. We're going to add one more to them here now. One more rule. You recall that when we had division, we subtracted the exponents. Simple enough. I'd also like you to notice that if my numerator is ever exactly the same as the denominator, I would get 1. So even if the numerator were x to the third and the denominator were x to the third, the numerator and denominator are exactly alike. Like 7 is the same as 7. We know that has to be 1. Okay? X to the fifth over x to the fifth has got to be 1. However, when I was dividing, like I did here, remember that I also could be subtracting the exponents. So if I had taken 5 and subtracted 5, like I did right here, I would get x to the 0. Now, we also recognize, though, that originally started off, it had to be 1. So this quantity had to equal 1. But if I subtracted the exponents, I got 0, which means this x to the 0 must equal the 1. That is why we get this last rule. Anything to the 0 has to be equal to 1. That means if I have 7 to the 0, it's 1. If I've got z to the 0, it's 1. If I got z to the -7th quantity to the 0, I multiply, I would get 1. If I have 7x squared y cubed raised to the 0 power, anything to the 0 power is always going to be 1. Always going to be 1. That's why we have this last law here. X to the 0 is equal to 1. A couple of last concepts then. What I'm trying to do here is to help you see the difference between how negatives, like this negative right here, is used. Technically, this parentheses is raised to the 4th power. What does that mean? Sorry about that, I need to cover that up. It really means that parentheses times itself 4 times. So it's a negative x over y, negative x over y, negative x over y, negative x over y. It's really a negative 1, negative 1, negative 1 every time. Well, if I take a negative 1 times a negative 1 times a negative 1 times a negative 1, I would get a positive 1. That negative basically canceled out. X times x times x times x would be x to the 4th. Y times y times y times y would be y to the 4th. I really don't need to write the 1, so it's x to the 4th over y to the 4th. Because the negative, here's the key part I want you to pick up. Because the negative is in the parentheses, the negative was raised to the 4th power. Compare that to this one. Notice this negative is not in the parentheses. This one was. Huge difference there. I want to say that again. When it's in the parentheses, it's raised to the 4th power. When it's not, this one really is only the negative out front. The negative is not in the parentheses. It's just one time out front. So I've just got x over y every time. No negative in the parentheses. So I've only got one negative, which means my answer will be a negative. I got x to the 4th over y to the 4th. So this one, because the negative was not raised to the power, it's just one negative that tails along. It's like a negative 1. I could have wrote a negative 1 there as well. Big difference between the two. Okay, some other easy ones here. I'm multiplying, so I need to add the exponents. So I need to take this exponent, even though it's got a variable, I treat it the same. I add it to that exponent, which means 5e plus 2e is 7e. That would be my answer. This one, I'm going to add the exponents. So I'm going to take 2s minus 1. Sorry about the scribble there. I need to add it to a negative 5s plus 7. So 2s plus a negative 5s is a negative 3s. Negative 1 plus 7 is 6. And that would be my answer. Okay. This one, 5e plus a negative 5e would drop out and you would get x to the 0 or 1. Okay. Next, we're going to review a concept that's a little bit different, but tied to exponents. So I'm taking the exponents here off the table, so to speak, and we're looking at scientific notation, a review of that. Mainly because there are some exponent rules that oftentimes come into play with scientific notation. You remember scientific notation had a purpose to write either very large numbers or very small numbers in a relatively compact position. It's a more efficient method. We're able to also multiply and divide very large numbers or very small numbers in this more efficient method. The standard form for scientific notation is any number between 1 and 10, could be including 1, multiplied times 10 raised to a power. Or I have this number, it's between 1 and 10, but it can include 1, not 10, raised to 10 to some power. I just went with p for a power. This is just an example I made up. This example is in scientific notation because my number 5.34 is between 1 and 10, and I've got 10 raised to some power. Technically, this number is 5. I need to move the decimal over 11 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's the number. Happens to be 534 billion. Writing it this way is a little shorter. It's why we say it's a more efficient method. Very large number. And I could have had a number here that had a lot more zeros. The scientific notation is a shorter way of writing it. Here's another example. This one was to a negative power. Technically, that means that that exponent had to be moved to the left 12 spots. So here we go. This is what it would have looked like. Moved it over 1, that was 1 spot, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's much more efficient to write it this way than that way. That's again one of the advantages of the scientific notation. But as I mentioned, you can also use it with multiplication. So for example, I could take this number right here. I could write this number in scientific notation. That would be 5.43 times 10 to some power. It's been moved over 1, 2, 3, 4, 5, 6, 7 spots to the left, which is a negative 7. I'm going to be multiplying that times this number, which I could write in scientific notation 4.56. It's been moved over 1, 2, 3, 4, 5, 6, 7, 10 to the negative 7. Then I could multiply these two numbers on my calculator, 4.53 times 4.56, or 5.43 times 4.56. I did that earlier. It's 24.7608. Times 10, I have to add these exponents. So I'm going to be adding the two negative 7s, and that's my answer. Notice the answer ended up not being in scientific notation because my number was not between 1 and 10. It's 24. I need to move that over. So I moved it to the left, which means I have one more negative here. So my answer would have been a negative 15. If I wanted to do a division problem, I could write this as 5.6. I'm moving it over to the right, so I've got 2, 5, 8, 11, and I believe 14. Divided by 7 times 10 to the 2, 5, 8. You can write it that way. Some of you might be more comfortable writing it like this, because really I'm dividing by that entire quantity. So I would be dividing by 7 times 10 to the 8th. Well, 5.6 divided by 7 gives you 0.8. When I divide here, I got to subtract my exponent, 6. This answer is not in scientific notation because this number 0.8 is not between 1 and 10. I got to move the decimal over. I moved it over from this side, making it a negative movement. So 6 plus a negative 1 would be 10 to the 5th power. Again, examples of using scientific notation with smaller numbers rather than the really large ones. That's all we have for today. So I'm again assigning this section, which I believe was, I forgot it, but I think I announced it earlier. Having a hard time keeping all of these straight. So I apologize for that. But it is section 8182. 8.1, 8.2 is assigned today on Wednesday, making it due next Monday, April 6th. Have a good rest of your day.